empat object binaries in Star clusters?
Yeah, so basically what I'm talking about here really is very much a work in progress, just sort of seeing sort of half-done stuff from PhD theses and so on. But it ties very much into what Rainer Schmerzen was talking about earlier and some of the work that we're doing on direct n-body codes with post-Newtonian terms in them. This is also very much focused on stellar mass binaries spiraling into each other, so it's a bit of change of pace from what we've been doing for the rest of the conference. So first I'm just going to briefly introduce more or less what we're doing and what we're interested in. I'll talk about the binaries in direct n-body codes. So this is sort of a more hard example of what Rainer was talking about earlier, although in slightly different systems. I'll then talk about trying to perform a similar analysis on binaries that come out of Monte Carlo simulations of star clusters. And finally, I'll just quickly summarize. So basically, the stellar mass compact object binaries that I'm studying are really promising sources of gravitational waves for the ground-based detectors, such as Virgo here, or LIGO and advanced LIGO. However, as we've heard, at least as a noise source, during certain phases of their inspirals, white dwarf binaries in star clusters at least provide a gravitational wave signature in the Lisa band, even if, as most people just consider it an annoying source of noise. But modeling it and modeling some of the components of it is probably still interesting from Lisa perspective. So basically, what are we trying to do and what are we interested in? Well, the gravitational waveforms, as we've said time and time again, are of course very sensitive to binary parameters. The dependence, of course, is very significant. And in particular, not just in the waveforms itself as well, but in time scales and event rates. This is a very old plot from a paper of Peters and Matthews in 1963 with the enhancement factor of power-radiated gravitational waves in an orbit-averaged sense over a circular orbit. So if you've got a circular orbit, it's 1. But if you get up to 0.8, 0.9, you're getting factors of 10 to the 2, 10 to the 3 enhancement in gravitational wave radiation. And this not only affects your gravitational waveforms, but very much your time frame for inspirals, and therefore your expected event rates. So we're interested in it in this situation. And as we've also seen, binary parameters are very definitely affected by their environment. And it's a bit different in star clusters than with supermassive black holes and galactic centers, because rather than having one or two objects that are many, many times more massive than the rest of the objects in the system, now you're dealing with objects that are inspiraling, interacting with a system of which they are of comparable mass to all the other objects in the system. So you get different effects, but still ultimately it is very environmentally dependent. And there's, of course, a very large parameter space to investigate. People are particularly interested in whether you have to actually worry about an eccentricity in the final inspiral and so on. So we sort of want to investigate this parameter space. So what we want to do is simulate stellar mass binaries in star clusters. We both want to investigate the event rates for gravitational inspiral binaries in star clusters. And then we want to get parameters for gravitational wave templates. So we not only want just event rates, where you could probably use sort of analytic formulas, we actually want to produce the final orbits and get orbital parameters as well. So how are we going to do this? Well, the method we've chosen is actually a full-blown post-Newtonian expansion of linearized field equations. A lot of people have mentioned post-Newtonian in one form or another during the conference. And Rainer actually wrote down what the formulas look like exactly. But basically, just to repeat again, this is a series expansion of linearized field equations. It's expanded in powers of the velocity of the relative velocity of the binaries over the speed of light. Certain of these terms vanish automatically, this one and this one in particular. And so then you're basically left with a post-Newtonian expansion, which is labeled in the relative orders. So there's your Newtonian, there's your first term that has a contribution, there's your second term that has a contribution, there's your third term that has a contribution. At present, we have up to 2.5 Pn included. The terms, the whole number terms are conservative. They deal with period shift, phase shift, and so on. And it's the odd number, or the fractional terms here that are radiative. This here is just a little schematic of sort of, if you have a circular orbit, then this is the orientation that these extra little accelerations have. So the 1 Pn sort of is out, opposes the Newtonian, the 2 Pn is in the same direction, and the 2.5 pulls away from your velocity, and so that's where you start losing energy. Now this is only in the circular case. It gets much more complicated when you're with an eccentric binary, but it's something to keep in mind. And basically, this is a fairly natural choice of method to include in a classical stellar dynamics code, because you can just, essentially, you've got the Newtonian acceleration, and you can just implement these as additional accelerations as corrections to the Newtonian acceleration. So at least in principle, psychologically, it's easy enough to do. Of course, the practice is very, very tricky. It's all sorts of tricks you run into, which we'll see. So the first attempt we have made with this is, well, ideally, we want to calculate these binary dynamics as part of a whole cluster simulation. You've got a live globular cluster, you've got live post-Newtonian dynamics for the binaries. Everything is being done as accurately as possible. So this is what we want to do. And so the approach we're using, as Weiner said earlier, is we work with this n-body series of codes from RSEF. Particularly, I'm working with n-body 6++, which is the version made for parallel computers and hopefully to run on this special purpose hardware. n-body 6++ includes a regularization scheme for the binaries, and therefore, and so the external forces are then applied as a perturbation to this regularization, and so then the Pn corrections are applied as a perturbation to the regularized binary. And as I mentioned earlier, we actually have at least a semi-working version of the n-body 6++ code with up to 2.5 Pn post-Newtonian corrections. For the central mass of black holes, we've got even further. We've got a much better working version. For the stellar mass, we're still working on it. You'll see why in a moment. But we actually can get some results. We've so far performed some simulations with no initial binary fraction, and even so, you can still get a few relativistic mergers. So the time units here, 1 is about a mega year. So this is about a giga-year in total in physical units. And we've actually enhanced the effect of relativity here by choosing a rescaling the system with a slightly smaller value of c, just to make sure that we can get some mergers and the thing is working. However, we have this working, so great, that's wonderful. However, we're still running into some problems, particularly with energy conservation. We're generally conserving energy quite well in the total code. But every now and again, there's scatterings in energy conservation that are quite bad. So still having to work on that. And it's in particular a little bit difficult because we have yet to find an order-by-order expression for the post-Newtonian energies that works with the Hermite scheme. Because with this, you require derivatives of acceleration, which then go back into the post-Newtonian energy terms, which then introduce higher order corrections in the lower order terms, and it can get a little tricky. But we're working on that. Really, a bigger issue is we're having difficulty running simulations with large numbers of primordial binaries. And this isn't to do with the post-Newtonian terms per se. It's got to do with the fact that the version of n-body 6++ we have right now doesn't have the most recent stability routines for sort of hierarchical triples and other binary systems. So when we throw large numbers of primordial binaries at it, the code just tends to crash. And it's not really to do with the PN, it's just to do with the stability of binaries in the code in general in large numbers. So this is something we're definitely working on, but at present we've put this approach on the back burner, at least for the stellar mass binaries, for a while, to approach binaries that we can get from other simulations which are already running fairly well. And what we've been working with so far is using the results of binaries that are produced by Monte Carlo models of globular clusters. And one of the nice things about this actually is, unlike direct n-body, where realistically we can only at present do 10 to the 4, 10 to the 5 particles or so, in principle with Monte Carlo codes you've got a full globular cluster there. You've got 10 to the 6 particles, you can run it, you can take a look at binaries. However, the problem with the Monte Carlo codes is essentially you're evolving the cluster using relaxation theory. And that means that the time steps you're taking are on the orders of dynamical times and relaxation times, all of which can be quite large in physical units, so the orders of megayears to gigayears. And these post-Newtonian binary dynamics and the mergers are happening frequently on the scale of megayears. So you can't actually resolve them individually in the Monte Carlo codes. Should mention, I thought I had it down here, but this is work that's actually done in close collaboration with Mirek Giersch in the Copernicus Institute in Poland. So we basically, from his code, we can get binaries at each Monte Carlo time step that are expected to merge by the next Monte Carlo time step. So that's what we get here. And so for each time step, we get a cluster binary population with realistic binary parameters for globular clusters. We can then take another code called BSE, and this isn't as sinister as it sounds. It's not bovine spongiform encephalitis. It's in fact the rather imaginatively named binary stellar evolution from Jerry Hurley. This is a semi-analytic binary stellar evolution code, but it includes quite accurately things such as Roche-Loeb overflow, tidal locking, perturbed binary evolution, and so on. And one of the things you have with stellar mass binaries rather than the supermassive ones is in this phase, definitely these other stellar processes are far more important for binary shrinkage than are the post-Newtonian terms. These are the much stronger elements. So we can put these binaries, which are just, they run the gamut of all sorts of stars, into this binary stellar evolution code, and then we evolve them until the binary is double degenerate. So at the end of this step, this is something we do ourselves, and at the end of this step, we have a series of binaries which run the gamut of combinations of white dwarfs, neutron stars, and black holes. Now, at this point overall, most of the star-to-star interactions in the evolution are now over. And so they're going to more or less evolve in a purely post-Newtonian sense after this. And so what we do then is we take these double degenerate binaries and do an explicit two-body integration until they merge. And so to actually produce the final Inspiral merger using a post-Newtonian treatment and to get full orbital information for the merger, and then we have data about relativistic mergers. So that's the plan. And for this segment here, I'm using a two-body code written by Ingo Berendsen, who is here. It's a Hermite fourth-order integrator, and it's got 1 PN, 2 PN, and 2.5 PN corrections. So this is a 2.5 PN accurate two-body integration code. And by doing this, we can get some rather nice results. So we can basically produce quite detailed information on binary populations in star clusters. So for instance, here's the result of what comes out of the binary stellar evolution codes. This is our initial distribution of doubly degenerate binaries. You can see there's some with a significant eccentricity still. So if they're going to circularize, it's going to be circularization through gravitational wave radiation. This is now in mega years, just to give you a more reasonable sense of units. You can see there's sort of two distributions here. And so these ones here will have been very massive early stars that become double degenerate very quickly, mainly high mass black holes, and then in principle merge quite quickly, as you can see. And then here are some of the ones that have taken a longer evolutionary path through a much broader phase of binary stellar evolution before they become double degenerate. And these ones here tend to be more white dwarfs in principle, white dwarf, or white dwarf neutron star binaries. So this is before we put them into the two-body code. And this is what we are getting out after running the explicit two-body integration. Note that there's fewer points on this graph than there are on this one, and that's because we haven't successfully evolved all of these through two-body evolution yet, and I will explain a little bit more about that in a moment. But you can see at this point, we don't have so many of the high eccentricity binaries, at least not yet. Although these are also the ones that started closer to each other, so they were already drawn from this distribution rather than this distribution. But you can see there's certainly non-zero eccentricities present here. You're getting up to eccentricities of 0.1, for instance, which is definitely of interest for people, I think, who are producing the templates. So we can get information both on the populations, but we can also produce detailed information on the inspiral of each binary that we're studying. So this is a particularly interesting binary because it's two black holes, very massive, 64 solar masses, 19 solar masses. This is the eccentricity as a function of time as we evolve it. So it actually starts out at a reasonable eccentricity and eventually spirals into an eccentricity of 0 or close to, but not before a fairly long period of evolution. And this is still just in the last few years of its evolution. So these things can maintain reasonable eccentricities for quite some time. There's just a separation. Again, it starts, this is an AU, so it starts at about 0.3 AU and then spirals in. And I'd like to point out again, as was pointed out earlier, we really here are taking binaries and evolving them all the way into merger. And so we can get the whole thing here from these PN codes. We've got everything down to a merger at this point. You can probably start to question right at the end here how accurate are the PN methods, but we can get really, really close to the merger, the last few inspirals with this method. We can carry it all the way through. Now, of course, I mentioned, as you know, always, there are issues, as I mentioned. None of our high eccentricity binaries, which are the ones that started with a wider initial separation, are in this final result. And that's because the inspiral of anything but close massive binaries in two-body evolution, of course, takes a very long time to do computationally. We've heard this too with some of the inspirals of the supermassive black holes as well. To actually compute the full inspiral can take a long time with a computer. So this is something that started. This is the same massive binary as before, but now started at an initial separation of about 25 AU. Now you've got 100,000 years here, and you can see it's inspiraled due to gravitational wave radiation, 0.1 of an AU or something like that. And this took, this is still running on the computer, and this is the result after about 4 days. So to actually inspiral something like this, it's going to take a mega year or two to inspiral, but in principle take a long time the way we're doing it right now. So again, we're looking at ways of fixing this. One would be to evolve them semi-analytically a little bit further in before we start turning on the full PN. However, the problem with that is you use Peters and Matthews kind of semi-analytic formulas. The problem with that is you start to lose orbital information at that point. And it's not necessarily much faster to actually numerically integrate these equations if you're trying to get the same degree of accuracy. The other thing that we can look at is doing different time steps in the different time step regimes. Because again, normally the way these things inspiral is they've got fairly flat phase, and then right at the end they plunge. So when there's not much change in the separation and semi-major axis, we can probably afford to take much larger time steps and then redefine our time step criteria for the final plunge. So again, this is something that we're looking at. But in conclusion, what I'd like to say is through both the direct n-body methods and the Monte Carlo codes, we now actually have two working methods for calculating post-Newtonian inspirals of realistic binaries in realistic globular cluster situations. Both of them we're having issues with, but none of these issues are really fundamentally physical issues. They just take playing around with the code and trying to make things more efficient. And so again, I'd like to reiterate what's been said earlier today. Here we really have a method for calculating, for getting sort of realistic binary parameters and realistic inspirals with at least a somewhat realistic treatment of general relativity. And so hopefully with this, we can then shed some more information on some of the likely parameters for the binaries that are going to be detected by our gravitational wave detector.